Hi, welcome to Office Hours. My name is Patrick Curran, and along with Dan Bauer, we make up Curran Bauer Analytics. In today's episode of Office Hours, I'd like to spend a few minutes talking about nonlinear trajectories and how we can estimate these within a growth curve model. In prior episodes of Office Hours, we've explored a couple of different topics within growth curve modeling where we've focused on linear trajectories, and here I'd like to expand those into nonlinear models that we can fit in either a structural equation modeling or a multi-level modeling. Most of what I talk about in this episode can be done in either SEM or multi-level, but there's one topic that only applies to the structural equation modeling approach. So briefly, where we've left off before is we can estimate a trajectory where we map some repeated measure y, maybe it's antisocial behavior, maybe it's substance use, maybe it's math ability in children, whatever our outcome is we want to build a model to connect the passage of time with the model-implied value of the outcome that's under study. What we've done thus far is focused on linear models. And so a line is defined by some intercept, let's just call it, say, mu alpha, to represent the intercept of the trajectory. And if we begin our time coding at 0, then that's the model-implied value of the outcome at the first assessment of our repeated measures. And then we had some slope of the line, which we can call, say, mu sub beta. And what that is like any line, it's the model-implied change in the outcome given a 1 unit change in the predictor. But there's a really interesting implication of this in growth models, is when we have an intercept and a slope in our trajectory, is that mu beta, whatever it might be, let's just make up a number and say it's 0.5, is whatever our outcome is a 1 unit change in age is associated with a 0.5 unit increase in the outcome. All right, what that means is let's say we've rescaled time to be 0 here to represent age 6, 7, 8, 9, 10, 11, excuse my writing over. What this means is if a child goes from age 6 to 7, the model-implied value of the outcome goes up 0.5, 7 to 8, 0.5, 8 to 9, 0.5. You can see the pattern. As what the general rule is with the linear trajectory, it implies that there is an equal amount of change that occurs between any two adjacent time points, age 6 to 7, 9 to 10, 17 to 18. It's equal no matter where in time that occurs. That, of course, is what defines a line, and there are a lot of advantages to that in the growth model because it's straightforward, it's easy to interpret, it's easy to understand, except it's only valid to the extent that our outcome that we're measuring approximately follows a linear trajectory. But here's part of the trick, is much of what we study in social science, behavioral science, health sciences, does not follow a linear trajectory. So for example, say that we are following young children, say entry to kindergarten, and we're studying reading ability, the acquisition of reading ability. What we might well find is that reading ability has a developmental trajectory like that, where let's say again that we scale it to start at 0, and again let's have that represent age 6. I have another video on coding of time if you're interested in that. But age 6, and then we have 1, 2, 3, 4, 5, 6, and so on. 1, 2, 3, 4, 5, all right? Where this represents age 6, 7, 8, 9, 10, up to age 11. So the lower numbers are the actual ages, and the upper number is how we code time in the model. What we see is, well, we still get an intercept, right? We can still call that mu alpha, and that's the model-implied value of the outcome when our initial assessment. But notice now that whereas the line implies that there's an equal increase per 1 unit change in age, no matter where in age that occurs, here we have a very different situation. Here, a 1 unit change moving from age 6 to 7 has a very large increase. But notice as we move, say, from 9 to 10, that's much smaller, and moving from 10 to 11 or even up to 12, there may be almost no change at all. And so what a curvilinear trajectory implies is the amount of change in the outcome per 1 unit change in time, the magnitude of that change depends upon where in age it occurs. So there can be larger change earlier, smaller change, negative change, or it could even begin to go down, depending on what we're studying. And so we need to build a model that expands the linear trajectory to allow for nonlinearity. But then here's where things get tricky, because there's only one line and we can define it by an intercept and a slope. There are many kinds of curvilinear trajectories that can exist, and some of these we can incorporate into our model and some we can't for various reasons because of restrictions within the structural equation model. Now what's nice is both within the multi-level framework and the structural equation modeling framework, there are a class of approaches we can use that allow us to approximate different kinds of form of nonlinearity. So I'm going to use the structural equation model as an example just because I can draw path diagrams for that, but the next couple of topics apply to multi-level as well. So we know that we can build a trajectory using latent factors. And again, these are in prior videos if you haven't seen those, but we can have our outcome y at age 6, at 7, 8, 9. Let's just stop there. These are indicators. Let's say wave 5. So we can put 1 here. And we know that to build a line, we can estimate, say, latent variable 1 that goes to all the repeated measures. And these all have factor loadings of 1, and this represents the intercept of the trajectory. All right, and we can have an eta, say 2, that has increments in value of, say, 1, 2, 3, and 4. And so what this implies is, again, we have age here, we have our outcome y here, and what we're defining is an intercept here, eta 1, and a slope, eta 2. All right, and then we can allow these to covary, and each of these has a residual variance in the usual way. All right, but what if that doesn't hold? What if there's some form of nonlinearity? Well, it turns out that a line is part of a broad member of nonlinear functions called polynomials. And it's a polynomial, technically it's a polynomial of degree 1. All right, that's what defines a line. Well, we can have a polynomial of degree 2. And what that introduces is what we've all seen at some point or another, which is the quadratic trajectory. And so we can have something like this, and we have now intercept in the usual way, eta 1. But now there are 2 components to change. It's not just constant change, is we're going to have what's sometimes called velocity and acceleration. That's what happens in a quadratic. And so if you recall, a line we can define as y is eta 1 plus eta 2 times age, right? Because it's constant. For a quadratic, we're just going to expand that where it's eta 3 age squared. So that's where we're going to bring in that curvilinearity. And to do that in the model, we're simply going to add another latent variable. We'll correlate it here and here, because we're going to correlate all of our latent factors. We'll label this eta 3, all right, and this 2 will go to the repeated measures. But the time coding on eta 3 is going to be the linear coding squared. So we're going to have 1, 4, 9, and 16. So each of these latent factors are going to get a mean. Those are going to be the fixed effects. Each one is going to get a variance. That's going to be the individual variability around the fixed effect. And then they all covary with one another, the intercept, the linear, the quadratic. These are a little trickier to interpret than the linear is because we have 2 components of change over time. So the intercept is always where the curve intersects with the y-axis when x is 0. But now the linear is the slope of the tangent line of the curve when the predictor is 0. This is sometimes called instantaneous velocity. It's a weird thing to think about because it's velocity, but at a fixed point in time. But we actually all do this ourselves every day when you're driving your car and you look down and you see what your miles per hour are at that moment. So right when you cross, say, a line in a crosswalk and you look down and it says 38 miles an hour, is you're going 38 miles an hour at that very point, right when you cross the line. So that's sometimes called velocity or instantaneous velocity. But then this quadratic component, the eta3, is the rate of change in that instantaneous velocity. And we often refer to that as acceleration. And so as the curve goes up, notice at every point, the slope of that line is becoming less steep. And so this would have a negative acceleration because the curve is going faster, change is bigger at the front end, and then it begins to get slower and slower. And at some point out there, it'll actually turn back down. Whether that does in our observed data or not is an empirical question, but the model implies with any quadratic that at some point it will turn back down. Now, there are other ways that we could expand this. We could add another eta4 to have a cubic, and what that does is it goes up and down and then at some point turns back up again, and we can do a quartic, which adds yet another. But often in applied research and the kinds of things that we all study is it tends to stop at a quadratic. Now the cool thing about this, which we get both within the multi-level model and the SEM, is the linear is nested within the quadratic, so we can do a formal test as to see whether we need the extra factor to account for nonlinearity or whether the linear model is sufficient. And so we can get a chi-square statistic with just the linear, chi-square with the quadratic. We take the difference between the two and we can get a formal test of whether this is a significant improvement in fit. So that's a polynomial. We can do a line, we can do a quadratic, we can do a cubic, and so on. It works very well. It's a parametric form that we know and we understand, but not all of our data may correspond to that. Is just because we want to have age and age squared doesn't mean that's how the pattern of our data is going to follow. And so there are a couple of other options that we have. The next one is what's sometimes called a piecewise linear. And let's say that we have some trajectory that's shaped like this, all right? Now, a quadratic may not fit this well because remember, a quadratic is always going to want to go toward infinity. It's either going to turn over and go down, or if it's a U, it's going to go up both ways. But that may not fit well here. What we could do is say, all right, I'm going to approximate this. I don't believe that the quadratic is what governed it, but maybe what, if I do this right, is let's say I were to fit one linear component that went up to about here, and then I fit a second linear component to here. Now this is kind of cool because what it is I'm embracing that I don't know what the parametric function is, but I'm going to approximate it with a combination of two linear pieces that have some knot here. This is where they're tied. And so the first, if we have age progressing here, the first piece is bringing the construct up, the outcome up as it goes on, and the second piece isn't contributing to that yet. It's just coming up. At the knot point, the first piece quits contributing to the model and the second piece takes over, and then it has a slope. Notice it has a linear slope. So here this slope might be, let's just make up numbers, it might be 0.75, but this linear slope might be 0.25. So they're both linear slopes, but this one is much larger, this one is smaller. Now we get fixed effects for those, we get random effects. There's individual variability in the acceleration here in the linear slope. There's individual variability in that. We can actually look at the covariance between the two of them. And we can play around with different ways of coding time in this, but what often happens is we'll have time where, let's say our factor loading is we have 1, 1, 1, 1, 1, all right? So we have, let me throw another one in there, 6 time points. Is the first piece might be 0, 1, 2, 3, 3, 3. So it takes it up to that not point. And the second piece is 0, 0, 0. And that's, so we'll have 0, 1, 2, 3. And then it kicks in at 0, 1, and 2. So that defines the slope of the second piece. And I won't draw it out here because you can see in the factor loading matrix here, these are the values that go on that path diagram that connect the latent factors to the repeated measures. Is we have 3 factors just as we did with the quadratic, but here we have an intercept, the linear of the first piece and the linear of the second piece. And there are all sorts of interesting things that we can do with that as well. Now, also, we can do this in the structural equation modeling, or we can do it in the multi-level linear model. Both of those are equivalent. This last option, we actually can only do within the structural equation model. And the reason is that we're going to access the factor loading matrix, and that doesn't exist within the multi-level model. In the multi-level model, we bring in time as a predictor variable, and in the SEM, we incorporate time through the factor loading matrix. So I'm going to redraw our SEM. All right, so let's do, say, 5 time points, 1, 2, 3, 4, 5. Now remember our linear, let's say that's 801, that's going to be our intercept, and that almost always stays unchanged. We always leave that alone, that's 1, all right? And then remember that for the linear, we just looked at this a few minutes ago, is we have 1, 2, 3, 4, and that's implicitly a 0. We don't usually draw it, but it's 0, 1, 2, 3, 4. Now the linear, we're fixing these to those particular values to define the slope of the line. Well, if the model doesn't fit well, or if the repeated measures don't follow either a linear or a quadratic, is they may want the model may call for values that are other than the ones that we fix them to, right? So we're making time progress. I'm going to go ahead and put this in as well as 0. All right, is we are saying that the means, the variances, and the covariances of the repeated measures have to follow this 0, 1, 2, 3, 4. Well, that may be too restrictive, and we can do what is sometimes called a latent basis model or a freed factor loading model. Is instead of fixing all of the factor loadings to represent a particular parametric form, we can freely estimate them from the data, just like we might do in a confirmatory factor analysis. And so instead of fixing these to 2, 3, and 4, we could remove that restriction and just freely estimate the parameters. And there are 2 ways that we can do this. We can fix the first 2 to 0 and 1 and then estimate the remaining factors, or we can set the first one to 0, the last one to 1, and estimate the interior factor loadings. The 2 models fit the same, the factor loadings are just scaled a little bit differently. But what this captures is, instead of saying that time has to move forward as 0 to 1 to 2 to 3 to 4, is it allows the model to select the optimal loadings that best account for the observed means and variances and covariances. And that's why it's called a freed loading model, is instead of fixing them, we freely estimate them. And again, the linear model is nested within this, and so we can test a difference in fit. This approach works well in many situations. The little bit of a payment that we have to make is we no longer unambiguously know what this represents. In earlier models, we knew that this represented a linear slope or a quadratic change in the rate of change. Here, it's individual variability in the propensity to over time. It's like a shape factor. And we simply don't know what the parametric functional form is, because it's kind of taking the best fit through the data as we give it off to the program. So those are three approaches that we can use for nonlinearity. As we have the family of polynomials, quadratic, cubic, quartic, however high you want to go or how much data you have. We have the piecewise linear. I only showed 2 pieces, but you can do 3 pieces, 4 pieces. It expands. Again, it depends on the characteristics of the data. And then we have a free loading model or latent basis function in which we allow the data to help govern what the optimal fit is. And however of these we incorporate, whichever of these we incorporate and identify as the optimal fit, then we would often take that model to the next stage where we incorporate predictors, covariates, time-varying covariates, things like that. Now, there are also a number of advanced methods that we could use here, a structured latent curve model and some other options, but those start to move into nonlinear constraints in the model, and we won't explore those here. So that's just a few minutes about nonlinearity and growth models. The polynomial and the piecewise we can do in either the SEM or the MLM. The free loading model is restricted to the SEM, and hopefully that's been of some use. So as always, thanks for your time.